Hello, and welcome to the 7th lecture on metaprogramming. What is metaprogramming? Well, in general, it just means writing programs that generate other programs. And in most programming languages, this is kind of an obscure feature, if it even exists at all. But in Lean, metaprogramming is actually quite an important part of the system, and that is mainly because tactics, of which you have seen quite a lot up to this point, are metaprograms, right? Recall that when you write a tactic proof of some lemma or something, then behind the scenes, the tactics generate a Lean term that has the right type. And after you're done with the tactic proof, you can write print and then the lemma, and then it'll show you the term that it generated. And this makes a tactic a metaprogram because, well, it's a program that generates programs. And you've already seen that tactics in Lean can do a lot of things. Some are very simple, like the assumption tactic, which just picks out the right hypothesis from the context without you having to specify it explicitly. Others are very complicated and very useful. For example, the simplifier, which does a whole routine and looks at all kinds of lemmas and sees which ones are applicable, etc., etc. But these tactics are all built on a common metaprogramming framework, and in this lecture we're going to show you what this framework looks like, at least some of the basics. I mean, we only have one lecture, so it's not going to be the full thing. But at the end, you'll be able to write some simple custom tactics that do some of the tasks that you would have otherwise had to do by hand, which can be very useful. The first example of metaprogramming that we're going to look at is not real metaprogramming, but it's kind of a step in that direction. And that step is tactic combinators. So up to this point, you've written your tactic scripts as just a list of individual steps. And now we're going to look at some techniques that you can use to shorten these tactic proofs and often make them more elegant and more readable. Sometimes also obfuscate them and make them less readable, but that's kind of a style question. So, for example, one thing you might have noticed is that there are proofs that are very repetitive, where you kind of apply the same tactic multiple times, and you might have asked yourself, okay, there has to be a way to shorten this. So, for example, if we look at this lemma, which is called repeat example, we have a lemma consisting of 4 conjuncts. And, well, the first thing we probably want to do is get one subgoal for each of these conjuncts. And so the way we might do it by hand, let's just comment out this thing for a bit, is to do, okay, we're first gonna apply and.intro, and then this is gonna give us 2 goals. So one of the goals is this even 4, and the other goal is the rest of the whole thing. And so, okay, let's skip the first goal for a bit, go to the second goal, and then here we apply end.intro again, and then this is gonna give us 2 goals. The first is even 7, and the next is the rest of the thing, and then we apply end.intro again. Okay, and now we should be done. And I've forgotten some commas per usual. Okay, now we're done. Okay, and now we have 4 subgoals, even 4, even 7, even 3, and even 0. But it turns out that Lean has a mechanism that automates this kind of thing so that we don't have to write this whole tree here. And that mechanism is called repeat. And you can see here, when we write repeat, apply end.intro, then the end result is exactly the same as what we had before, 4 subgoals for each of the 4 conjuncts. So tactic combinators are called combinators because they are tactics that take other tactics as arguments. And the way we write this in Lean is we write the name of the combinator, here repeat, and then we write curly braces, and in those curly braces we put the tactic that is supposed to be repeated. And now what the repeat tactic combinator does is fairly simple. So first it applies this inner tactic, the apply. It applies this tactic to all current goals, and then this tactic may generate new goals, and then repeat is gonna again apply the inner tactic to all of these new goals, and so on and so forth. And the whole process stops when this inner tactic fails. And this is kind of an important concept. So up to now, you kind of have only written tactics that don't fail, because, well, if a tactic fails, you've probably made a mistake. But as soon as we work with tactic combinators, a failure of a tactic is actually quite a useful concept, and we often want our tactics to fail. So for example, repeat, right? If it's not supposed to run forever, then the inner tactic has to eventually fail on all the sub goals that we apply it on. Yeah, in this case, what happens is, so it first applies the end.intro, then we get two sub-goals. One is this even 4, and the other is this guy. Then it applies end.intro on the first sub-goal, but there apply end.intro fails, because this is not a conjunction. And so the process stops, and then it applies end.intro on this guy, and then this succeeds, generates two new goals, and so on and so forth, until we've kind of dismembered the whole thing into its conjuncts. Okay, and then we can look at another use of apply, right? So recall that even has this add to lemma, which says that if a number k is even, then the number k plus 2 is also even. And that looks like a useful construct here, right? Because all of these goals are of the form even and then some literal. So we might be able to prove them by just applying this add to lemma. And indeed, if we do that, then you can see that we get a bunch of very simple goals here. So for example, the first sub-goal even used to be even 4. Then the repeat applied even.add2. So then we just need to prove even 2. And then it applies it again. So now we need to apply even 0. And now, of course, even.add2 doesn't apply anymore. And so it leaves us with the goal even 0. Similar for the second sub-goal here, even 7 reduces to even 5, reduces to even 3, reduces to even 1, and then the thing is not applicable anymore, and so it doesn't reduce any further. Okay, so this doesn't solve the goals yet, but we can do better. And the way we can do better is by using another combinator, which is called or else, and is usually written with this funny symbol, less than, bar, greater than. And what this combinator does is it takes two tactics, and it first executes the first tactic. If that tactic succeeds, then we're done. If that tactic fails, then it tries to apply the second tactic, and if that tactic succeeds, then again the whole combinator succeeds. If that tactic also fails, then the whole combination fails. So let's look at an example here. So same lemma as before, and the same first step, so we get these 4 sub-goals as before. And now we write repeat, and then here in the repeat we say, okay, in each step of this repeat loop, either apply even.add0, or if that fails, apply even.0. And so what that leaves us with is only 2 sub-goals. And the difference to before is, so before, when we did only the apply even.add2, it left us with these 2 even 0 sub-goals. But now, since we also apply even.0 in the loop, it solves these two even 0 subgoals and leaves us with only the even 1 subgoals. Okay, in the rest of the section we're going to go through some more combinators. I'm going to go a little more quickly right now because I think you probably got the general gist of things. So, first combinator that we're going to look at is iterate, and this is very similar to repeat, but it doesn't work on all goals. It only applies the inner tactic on the first subgoal. So it applies it on the first subgoal and then again on the first subgoal and again until the tactic fails. So let's look at what it produces for our case. So same lemma, same first step, and then after the iterate what we get is, so the first subgoal, even 4, has been solved, right? Because it applied add 2 twice and then it applied 0. Okay, and now the first subgoal is this even 7, and this was simplified because it applied even.add2 a bunch of times until we are left with even 1. But in this state, obviously neither even.add2 nor even.0 applies anymore, and so the iterate stops. And yeah, we're left with these 3 subgoals instead of just 2 subgoals like we had before. Okay, next combinator is all goals. All goals applies its argument exactly once to each of the goals. So this is saying, okay, I have a tactic, I want to apply this tactic once to each of the goals. And all goals succeeds if and only if the inner tactic applies to each goal that we apply it to. So here's an example of where this doesn't happen. So same lemma as before, and we say on all goals apply even.add2, and it fails, and it tells us invalid apply tactic, something something. The error message is not super helpful, to be honest. But essentially the reason why it fails is that even.add2 is not applicable for this subgoal here, the even 0, and so all goals fails. What can we do about that? If we want to say, okay, apply to all goals, but if the tactic is not applicable, then no harm done. This is what the try combinator is for. And so try is a combinator that takes a tactic and says, okay, I'm going to execute that tactic. If it succeeds, great, but if it fails, then I don't fail, but I do nothing. So it tries to apply the tactic, but if the tactic doesn't succeed, it does nothing. And so we can see the effect of this here. So same lemma, same first step, and we say all goals try to apply even.add2, and now this succeeds, right? Because on the last subgoal where it previously failed, it tries to apply even.add2, fails, but that doesn't matter because we've written try here, and so the whole tactic in the end succeeds. We can achieve a similar effect with the next combinator, which is called any goals. And any goals is similar to all goals, so it applies the inner tactic to every goal, but it already succeeds if the inner tactic succeeds on any of the goals. It only has to succeed once, it doesn't have to succeed on all of the goals. So again, we can try this here, and we get the same effect as before. So our goals were reduced to even 2, even 5, even 1, and the last goal was not reduced because apply even.add2 failed, but the whole tactic still succeeded because apply even.add2 succeeded on the 3 first subgoals. Alright, and then the last combinator that we're going to look at is called solve1. And solve1 is a bit of a curious thing because it makes a tactic fail, which is not usually what you want, but sometimes it is. Because sometimes you want to know that a tactic succeeds in solving a subgoal. So you want to say, okay, run this tactic, but only if it solves the entire goal. And if not, we want to try something else. So here's an example of this. Same lemma, same first step. And now we say, okay, for any goals, apply the following tactic. Repeat this apply even.add2 or apply even.0, but only if it solves the goal. And let's see what this leaves us with. Okay, so the first goal and the last goal were solved, right? Because on these goals, this repeat thingy here already solves the whole goal, and so that's cool. But on the middle two goals, this repeat thing fails to solve the goal, mostly because the goal is actually unprovable. And so in this case, the whole solve1 invocation here fails. And so the effect of this is that it leaves the two goals alone, right? When we do the repeat thing without the solve1, then we're gonna get goals even1 and even1 here, because it still simplified them to some extent. But since we wrap them in the solve1, it's an all or nothing thing, right? It says either you solve the goal or don't do anything with the goal. And in this case, that's not super useful because the goals aren't super useful, but you can probably imagine this can be useful in some situations. A quick word of warning about these combinators. So all of these looping combinators, repeat, iterate, all goals, any goals, and particularly the first two, repeat and iterate, can easily lead to infinite loops. Because, well, they like, if you write repeat, but then the inner tactic never fails, then repeat is going to happily continue applying the inner tactic until basically lean runs out of memory. And here's an example of this. I can't easily show you the example because, you know, lean's gonna crash. But if you uncomment this at home, then you're gonna see that it's gonna loop infinitely and eventually lean crashes. And the reason for this is that this not.intro lemma happens to apply to this goal indefinitely, right? So if we apply to the goal, then we get something that looks like a not again, and so on and so forth. And so this tactic never fails, and so the repeat never stops. And yeah, you have to be a little careful about that and make sure that your inner tactic actually fails at some point. Now, to close out the section, here is a first example of an actual tactic that you can write. And we're going to discuss this in much greater detail in the next section. So what does all of this mean? What is the meta? What is the do? Why do we have to write tactic everywhere here? But just to close out this section, I wanted to show you how these combinators translate into a definition of a custom tactic. So you can maybe see here that the structure of this thing is very similar to the combinator proof that we did above, only with some kind of syntactic replacements. And we write this as a meta def, which means that we can later on use it as a tactic. And so here we have the same lemma again, and now we can write intro and even, and then it's gonna transform this lemma like the tactic that we saw before did, and it's gonna leave us with two sub-goals. And yeah, in the next couple of sections, we're gonna dive into all of this stuff up here. And so we're gonna see how to actually write these tactics and how to move from combinators to real metaprogramming.